important thing that we do with logarithms is we use properties of logarithms, and this is really, I think, the true power of logarithms. This is why we spent so much time talking about it. Our skills will continue to increase because we're going to use these properties to solve more complicated equations, both with and without the calculator. So let's look at some of the properties here. First of all, we have the common logarithm. This isn't really a property, but more of a notational thing. Log base 10 of a number, I'll say log base 10 of m, is what we're going to mean when you see log of m with no base written. You have your natural logarithm, where you're using base e, Euler's number, which is 2.71828, and it keeps on going. The log base e of a number is what I'm asking you when you see natural log of m. This is our favorite property ever. If I have the log of a number being raised to a power, then this is the p in front of the log property. You can bring the exponent down in front of the log. So instead of your log of a number raised to a power, you bring the power down in front, and it's the power times the log of that same number. This is definitely the most useful property. We're going to make great use of it. Some other properties that are important, I think these next two, they go high on my list. But I see students misusing these a lot. I think it's because they don't quite understand what the property is saying. So let's look at this one carefully. If I'm taking the log of a multiplication problem, if I'm taking a log of a product, so m times n, that log can be rewritten. It can be broken into two logs. I write it as the log of the first term, factor, plus the log of the second one. So let me say that one more time. If I'm taking the log of a multiplication problem, it is going to be the log of the first number plus the log of the second one. Biggest mistake I see is I see students that will mistakenly write the log of m times n is equal to the log of m times the log of n. That is not true. Don't do it to yourself. It is going to cost you dearly. You need to make sure that you've got this one straight in your head. Well, if multiplication becomes addition, then it hopefully should work out that division becomes subtraction, and that's absolutely true. The log of a fraction, the log of a division problem, can be rewritten as the log of your numerator minus the log of the denominator. We also have the property that my log base b of 1 is equal to 0. So for any base, log base 2 of 1, log base 3 of 1, log base 112 of 1, it'll be equal to 0 because any base raised to the power of 0 is equal to 1. Another one that we use, and some students use this inappropriately, if you have a log of a number, a term, an expression, exactly equal to the log of another number or another term, then you can cancel out the logs on both sides, leaving you just m is equal to n. But it absolutely must appear as the log, not 2 times the log, not the square root of the log, nothing other than the log of a number or an expression equal to the log of another expression. Finally, you have a change of base log. If you are ever being asked to find, say, the log base 7 of 9, log base 7 is not something you can do in your calculator. Your calculator is equipped very nicely to do log base 10 and natural log. Here we've got log base 7. You can't do that nicely on your calculator unless you know this change of base formula. The change of base formula says that the log base b of a, so b is my base, a is what I'm taking the log of, is exactly equal to the natural log of a divided by the natural log of my base. That'll work all the time. So if I was trying to evaluate the log base 7 of 9, what I would do is I would take the natural log of a, which is 9, and I would divide it by the natural log of 7. I would pop those into my calculator. The result will be what the log base 7 of 9 is. Those are the properties. Let's start using the properties. Okay, we're going to go relatively quickly through these, but we have a typical exponential equation that needs to be solved. I have 10 raised to the 5x plus 2 power is equal to 3. The goal is to solve it for x. Now, of course, if it's a calculator active question, you could easily type in what's on the left for y1, type in what's on the right for y2, find the intersection point, you'd be done. I want to solve this problem without using logs. So let's do this. I have 10 raised to the 5x plus 2 power is equal to 3. What we're going to do is we're going to take the log on both sides. So since this is base 10, the natural one to select is log base 10. I have the log of 10 to the 5x plus 2 power is equal to the log of 3. I don't care what the log of 3 is. It's a decimal number. I can look that up in my calculator if I need to. But let's look at how we're going to solve this for x. I have the log of 10 being raised to a power. This is a great example of that p in front of the log property. I'm going to bring the 5x plus 2 down. Since that entire 5x plus 2 must multiply the log of 10, I'm going to use parentheses. That's going to be equal to the log of 3. Although I don't know what the log of 3 is off the top of my head, I should know the log of 10. Log base 10 of 10. 10 to what power is equal to 10? You're right, it's equal to 1. So I now have that 5x plus 2 is equal to the log of 3. I no longer need the parentheses, so you can just erase those if you'd like. I'm going to solve it for x. All I have to do is subtract 2 from both sides. I'm going to divide both sides by 5. I'll have negative 2 plus the log of 3 divided by 5. If you'd like, you could write it as x equals negative 2/5 plus 1/5 the log of 3. Any of those representations is fine. Happy with it? Move on to the next one. Okay, this next one. We have 2 raised to the 3 minus 2x power is equal to 7 to the x plus 1. I have a base 2 and I have a base 7, so unfortunately base 10 and base e not going to be so helpful. Since we used log base 10 last time, I'm going to use the natural log this time. You certainly don't have to use the natural log. For me personally, it's the one I like the most. We use it a lot in AP Calculus. You've got a nice connection between the natural log and the exponential. Natural log of 2 to this power equals the natural log of 7 to that power. I'm going to p in front of the log twice. So now I have 3 minus 2 times x equals the natural log of 2 is equal to x plus 1 times the natural log of 7. I need to solve the equation for x, but I have an x over here and I have an x over here. I have an x on both sides of the equation. If we were solving a nice algebra problem, let's kind of go off on the side here, we'll call this algebra land. If I was solving the equation 3 minus 2x is equal to x plus 1, all we would do is we'd move the x's to one side. We move everything that doesn't have an x to the other. In this case, we'd subtract x from both sides. We would subtract 3 from both sides. Those cancel out. Negative 3x equals negative 2. You would then divide both sides by negative 3, so x equals 2/3. Let's repeat the process over here. I have 3 minus 2x times the natural log of 2. I'm going to distribute this natural log of 2 through the parentheses. So now I have 3 times the natural log of 2 minus 2 natural log of 2 times x equals natural log of 7 times x plus 1 times the natural log of 7. Terms that have an x I want on the same side, so I want this term over here, the negative 2 natural log of 2 times x, and the natural log of 7 times x, I want those on the same side. I want all the terms that do not contain an x on the other. So 3 natural log of 2 and this natural log of 7, I want those on the same side. Can make that happen. This term stays. Negative 2 natural log of 2 times x minus the natural log of 7 times x, taking care of that one and that one, is equal to the natural log of 7 minus 3 times the natural log of 2. That's a number and that's a number. Both of these terms have an x, so I'm going to factor out the x to get negative 2 natural log of 2 minus the natural log of 7 is equal to natural log of 7 minus 3 times the natural log of 2. I have x times this number is equal to this number over here. What am I going to do? I'm going to divide. So we're going to have that x is equal to the natural log of 7 minus 3 times the natural log of 2 divided by negative 2 natural log of 2 minus the natural log of 7. We're going to resist this temptation. I'm sure somebody in the audience is tempted to cancel out the natural log of 7s. Because you have that negative sign, it's holding these two terms together. You can only cancel out a natural log of 7 if you have a natural log of 7 as a factor of both terms. We don't have that, can't cancel. Same thing with the natural log of 2. It's not a factor, can't cancel it. So as ugly as this might be, that's your final answer. X equals natural log of 7 minus 3 natural log of 2 divided by all this. If for some reason you needed an exact numeric, not an exact, if you needed a number answer, a decimal answer, I would just type this into my calculator, being very careful with placement of parentheses. I need parentheses around the numerator divided by the denominator in parentheses. If I don't have parentheses for the numerator and parentheses for the denominator, we're going to get the wrong answer. And we're done. So instead of an exponential equation, now I have a logarithmic equation. I have the log base 2 of this entire expression, x squared minus x minus 2 is equal to 2. I have a logarithmic equation. What we're going to do is we're going to keep in mind that any log problem, when I ask you the log base b of some number, what's that equal to? We have an equivalence. We can write it as the base raised to that power is equal to x. Let's see how this property over here, this equivalence, is going to be helpful. Instead of writing log base 2 of x squared minus x minus 2 equals 2, I'm going to take my base raised to this power is equal to this guy over here. So 2 squared is equal to x squared minus x minus 2. Now I'm out of the land of exponentials and logarithms, and I have arrived nicely at a quadratic. If I'm going to solve a quadratic, I want to get it equal to 0. I'll subtract 4 from both sides. X squared minus x minus 6 is equal to 0. I can go through and build mama a diamond to do the factoring. I can do the box. I can just factor it in my head. However you're going to choose to factor it, that's fine. Since that's not the purpose of this video, I'm just going to jump to x minus 3 times x plus 2 is equal to 0, which means that x equals 3 or x equals negative 2 are potential solutions. And the reason that I say these are potential solutions, or these are candidates for solutions, is you always want to make sure that you check these values in the original problem to make sure that they work. So let's do the check step. My check, if x is equal to 3, we're going to go back. We're going to evaluate the original equation. So I need the log base 2 of 3 squared minus 3 minus 2. I want to know, is that really equal to 2? Well, let's reduce what's inside the parentheses. 3 squared is 9. 9 minus 3 is 6. 6 minus 2 is 4. The log base 2 of 4 is actually equal to 2. Check. X equals 3 is definitely a solution. Now let's go over to x equals negative 2. The check step over here. I want to find the log base 2 of negative 2 squared minus negative 2 minus 2. I want to know, is that equal to 2? Negative 2 squared is 4. 4 minus a negative 2, that brings me to 6. 6 minus 2 is 4. The log base 2 of 4 is equal to 2. Check. Both of these are actually solutions. Now, what might cause one of your candidates to not be a solution? Well, if when you plug it back in, you're now being asked to find the log of a negative number, Negative numbers are not in the domain for the log function. It wouldn't be a solution. We'd call it an extraneous solution. Even though this is a negative number, that's fine, because when I plugged it into the original equation, I was taking the log of a positive number. Both are fine, no extraneous solutions. Be on the lookout for those. Okay. Now we have a slightly more complicated exponential. We have e to the x divided by 1 plus e to the x is equal to 4. A lot of ideas out there. When I first see this problem, I am tempted to cross multiply. I can rewrite the 4 as 4 over 1. I can then cross multiply to eliminate the fraction. That is one of my favorite tricks. I use that as often as I can. So maybe you see this cross multiplication. Maybe what you see is not cross multiplication, but you see an equation that has a fraction in it. And you're what I love to call them fraction killers. To be a fraction killer means that you multiply the entire equation, both sides, by the common denominator, so that the 1 plus e to the x cancels out. Makes the problem a little bit simpler. Like that, that'll work as well. Maybe what you see is you see that you can take the natural log on both sides. The natural log has nice properties. We have cancellation with e when they're right next to each other. We have the natural log of a fraction. We have a property for that. In fact, let's actually try solving it that way. So I'm going to take the natural log on both sides. Let me erase all that. Natural log of e to the x divided by 1 plus e to the x is equal to the natural log of 4. My property for logarithms here tells me that I can take the log of a fraction and rewrite it as the natural log of e to the x minus the natural log of 1 plus e to the x, and that must be equal to the natural log of 4. Great. The natural log of e to the x, I can use my p in front of the log property. X times the natural log of e minus the natural log of 1 plus e to the x is equal to the natural log of 4. Natural log of e, I'm really asking you, my base of e raised to what power is equal to e? That's just 1. So x minus the natural log of 1 plus e to the x is equal to the natural log of 4. Okay? So we took the natural log on both sides. We used the properties for logs. We've now gotten to this equation where we have x minus the natural log of 1 plus e to the x equals natural log of 4. Stop and look here. We've got the natural log of a sum. We don't actually have any properties for the natural log of a sum. I don't have a way to break this up. I can't, absolutely cannot write it as the natural log of 1 plus the natural log of e to the x. Because I don't have the natural log and the e right next to each other, I can't cancel them out. I can't bring the power down. Unfortunately, we're stuck. Now, we're stuck. This method didn't work. Let's go back and try another method. Let's see what other options we have. Earlier, we discussed maybe what we want to do is cross multiply. I think that's really going to be the way to approach it. This idea seemed like a good one. It seemed valid. It looked like it was going to get me somewhere. Didn't work. So I'm going to cross multiply. That's going to be my next idea. I cross multiply. E to the x times 1 is e to the x. 1 plus e to the x, all of that gets multiplied by 4. Okay, looks simple enough. I can distribute on the right. 1 times 4 is 4. E to the x times 4 is 4 e to the x. Now I have an x in the exponent over here, an x in the exponent over here. What I can actually do, and this is going to be super helpful, is I can subtract e to the x from both sides. They are like terms. I'll have 0 equals 4 plus 4e to the x minus e to the x is 3e to the x. I need to solve this problem for x. Well, how am I going to do that? I can subtract 4 from both sides. I can then divide both sides by 3. So I'll have negative 4/3 equals e to the x. We have a property for natural logs, or for logs in general. I can take the natural log on both sides. Natural log of e to the x. I bring the x down in front, and I get that the natural log of negative 4/3 is equal to x. Now wait a second. Didn't we just have a conversation about domain restrictions with logs? X, the variable I was trying to solve for, is equal to the natural log of negative 4/3. Since negative 4/3 is not in the domain of the log functions, I'm actually not able to solve this problem. This would be an example of a non-real solution. Some people might like to call it an extraneous solution, but this equation has no solution using real numbers. Later on, we can talk about complex numbers and all of that, but that goes well beyond the focus of PreCalculus or AP Calculus. So this problem has no solution. I think this is our last one. We have 2 times the natural log of 3 plus the natural log of 2 equals the natural log of 5 plus the natural log of x minus 2. Let's see. 2 times the natural log of 3. The natural log of 3 is a number. It's a number I can get out of my calculator. It's not one that I know in my head. But I do have a property for logs that says if what's the property? It's the p in front of the log property. If I have the log of something raised to a power, I can bring the power down in front so that it's equal to p times the log base b of x. Because this is a mathematical equivalency, I can actually reverse it. I can take the p that is in front of the log and bring it up as my exponent. How does that help? That means we can bring that 2 up here, and I can rewrite this as the natural log of 3 squared plus the natural log of 2 is equal to the natural log of 5 plus the natural log of x minus 2. So we have the natural log of 9 plus the natural log of 2 equals the natural log of 5 plus the natural log of x minus 2. My goal is to find x. In order to find x, we're going to have to get rid of everything else. We're going to continue pushing on these properties of logs. Natural log of 9 plus the natural log of 2. We have a property that says that that is the same thing as the natural log of 9 times 2. So we now have natural log of 18 equals the natural log of 5 plus the natural log of x minus 2. If still my goal is to solve it for x, I have to get rid of everything else. Well, what about if we subtract the natural log of 5 from both sides? We now have natural log of 18 minus the natural log of 5 is equal to your natural log of x minus 2. Just like we can combine 2 logs that are being added together as the log of the product, we can take a log minus a log and make that the natural log of a division problem. So the natural log of 18 over 5 is equal to the natural log of x minus 2. I have a log equal to a log. The base is the same on both sides. I have nothing in front of the logs. I can use that cancellation property. 18 over 5 is equal to x minus 2. I'm going to add 2 to both sides, and we're going to get 18 divided by 5. That's 3 3/5 plus 2, 5 3/5. You can go back, you can plug it in. Really all we care about is, will this candidate for a solution work in the original problem? Will it cause me to violate a domain restriction? If x is equal to 5 3/5, there's nowhere to plug it in here, or here, or here. The only place I plug anything in is over here. 5 3/5 minus 2 is 3 3/5. That's a positive number. Great, I can take the natural log, no problems. This actually is a solution. No domain restrictions to worry about. The last 2 things that we often do with logs is we look at Investment problems. We look at growth problems. This past year, we looked at exponential growth and decay. We have looked at bank deposits, where you are compounding interest at the end of every month, which makes it a discrete problem. We've looked at bacteria growing in a petri dish. That growth happens all the time. It doesn't happen on a scheduled basis. It's constantly happening. That's a continuous growth problem. So let's look at this one. Problems which involve populations, radioactive decay, basically anything that involves growth or decay happening on a continual basis will be modeled using the function A equals P times e to the RT. A is the amount present at time t. P is your principal. The principal is how much you have at t equals 0, your starting time. R is your growth rate if R is greater than 0, and we're always going to express these rates as decimal numbers. So if I tell you that the growth rate is 8%, well, then that means that R is going to be 0.08. We're going to refer to it as a decay rate if R is less than 0, and T is going to be time. Usually measured in years, but depending on the problem, it could be days, it could be hours, it could be anything, but you do want to look for consistency in your units in a problem like this. This is how we handle continuous growth, continuous decay. We're not actually going to work out an example right now. There are several others available in your textbook or in your class notes, or even check out some of the other videos my students have created for specific examples using A equals PE to the RT. If we're looking at discrete compounding, and this is more what you're going to look at if you're looking at investment banking, credit cards, problems like that. It's a different formula. It's a bigger formula. We don't use this one as much, but it works pretty much the same way. We have A. A is, again, the amount present at time t. P is your principal amount. That's how much you have at time 0. R is, again, your growth rate. If R is greater than 0, it's your decay rate. If R is less than 0, T is still time. The new piece for us is this N. N is the number of compoundings that are going to happen. Say that we're measuring time in years. If you were told that the bank is compounding interest monthly, then N is the number of times we do that compounding in 1 unit of time, in 1 year. So if we're looking at monthly compounding, then N is going to be 12. Other compoundings that occur regularly, we talk about quarterly compounding. If quarterly compounding over the course of a year, N is going to be 4. You could be compounding daily. N will be 365. You could be compounding semi-annually, twice a year. You could be compounding hourly. Probably not going to happen in a real-life situation. But hourly, you would take 365 days in a year. You would multiply that by 24 hours in a day. I believe the result there is 8,760. N would be 8,760. You could play this game minutely, secondly, in any unit of time that you would like, but N is the number of compoundings. From there, we take all of that and we plug it into A equals P, parentheses, 1 plus your growth rate divided by N. You take this 1 plus R over N and you raise the whole thing to the N times T power. What you're doing is you're taking your principal times this sort of growth rate factor to however many compoundings are going to occur. If you are compounding quarterly for 5 years, that means you would have done 20 compoundings. You take your principal times this factor 20 times, and that would give you the amount that you have at time t. So now we get to the final problem, and this is actually not one that I am going to work out for you. Instead, it is something that I'm going to read to you. I'm going to set this up. This is a great extra credit opportunity for anyone who is in my pre-calculus class. If you're not in my pre-calculus class, I can't promise what your teacher is going to do for you. But this is the level of problem that we expect at this point in your pre-calculus career. This showed up on last year's final exam. I'll just read it to you. A learning curve is a graph of a function that measures the performance of someone learning a skill as a function of their training time t. At first, the increase in performance is rapid. I'm learning to type. In the beginning, my speed increases very quickly. I go from 5 words per minute. Maybe after a couple of days, I'm at 15 words per minute. I might even get up to 30 words per minute by the end of the week. My learning curve, I've learned a lot in a short period of time. Sadly, that doesn't continue forever. Then, as performance increases, it approaches a maximum rate. Now, the rate of increase in performance decreases. So how quickly you're learning new things starts to slow down. You're still learning, your typing speed getting better. Maybe you've gone from 58 words per minute to 59 words per minute over the course of a week or two. Maybe you're at 60. But it's good. You're going to start to see it starts to flatten out. It has been found that the function p of t equals m minus c times my exponential, Euler's number, to the negative kt power, where k and c are positive constants and c is some number less than m, is reasonable for a reasonable model for learning. For a pole vaulter in training, the learning curve is given by this function p of t equals 20 minus 14 e to the negative 0.024 t power, where p of t is the height measured in meters. The pole vaulter is able to pole vault after t months. In part A, determine the value of p of 6 and interpret its meaning. Oh, and by the way, this is a calculator active question. B, find the average rate of change for the function p of t on the interval 10 to 11. Again, be sure to explain the meaning of your answer. C, using your knowledge of logarithms, solve the equation p of t is equal to 10. Be sure to show all the work that leads to your answer. What does this mean in the context of this problem? For my students who might consider doing this for extra credit, if you're going to solve this equation, p of t is equal to 10, on your first pass, feel free to use your graphing calculator. You can do the intersection method. But in order to qualify for the extra credit, you have to pay attention to the instructions, which is using logarithms, only logarithms. Part D, over what time interval will the pole vaulter be able to successfully make a jump, which is between 9 meters and 12 meters? And finally, find the value of the limit as t approaches infinity of p of t and describe its meaning to this problem. If you can complete this problem using great notation and good units, turn this into me prior to your trimester exam, I will definitely use this as an extra credit opportunity for you. Good luck. And this is my last slide.